Okay, great. Hello, everyone. Today, I'd like to share with you on the recent advances and future challenges of applying machine learning in self-driving. First, I would like to watch a short video, although we drive every day, but here we'd like you to focus on this short video and understand exactly what is the problem we're actually trying to solve. So our mission is build a self-driving car that drives much better than average human. Look at these scenes. As you can see, there are people and other human agents all around us, right? They could be driving a car, they could be riding a bicycle, they could be just walking around. And we also need to recognize all the traffic signs, right? There are stop signs, there are traffic lights, and there are all kinds of situations we have to handle. Let's look at this car, right? It's actually backing off, so we really need to understand what this car is doing, right? So how can we actually build such a system that's much better than average human driver? What do we need? How do we handle all these complex situations, right? I'm sure you all have experience in Beijing. We probably have much more complex situations. Well, there is a hardware story, and there is also a software story. Let's look at the hardware. So here's your self-driving Uber. As you can see, on the top, we have LiDAR, which generates 3D point cloud data, right? That's 360 degree. And we also have RGB cameras that also give us a 360-degree view. And besides LiDAR and RGB cameras, we also have radars. So it's safe to say our hardware in the car can do much better sensing than our human sensors, namely our eyes and ears. Well, what about the software? Can we actually manually write the software to handle all the complex situations in the scene? Well, I think all the self-driving car companies, probably none of them are trying the manual approach. And here is what machine learning came into the picture. And we can actually leverage huge amount of data to train our machine learning model to solve all these complex problems. What are the recent advances in machine learning, and what are the results? Let's look at some of the major problems. The first major problem we need to solve is 3D object detection. So given the LiDAR 3D point cloud data on the top of the image and RGB camera at the bottom, well, we need to produce our 3D bounding boxes for each object, and what is the object in the bounding box, right? Could be car, could be person. How do we solve it? Well, we use deep learning models. Here's a deep learning model in action. We see we have detected all the cars around us, and we're putting a pretty tight-fit bounding box around it. We have come a long way in 3D object detection. I think we have solved this pretty well. Well, what are the other problems? Besides detecting them, I also need to track them and understanding a short time scale within a single second where they're going to be. That is tracking. Well, people typically use Kalman filters to do tracking, but here we have a deep model, and the same number represents the same car in multiple frames. As you can see, our deep models can actually do pretty good tracking. Well, besides detection and tracking, we also need to understand where are these objects going to go, right? So that our planner can plan through these objects in motion. Not surprisingly, we're also using deep learning model to solve the prediction problem. So here is the prediction system in action. As you can see, each dynamic object can actually have multiple possible trajectories, and we have to actually predict multiple trajectories and rank them. As you can see, we get closer to the intersection. We have multiple trajectories. Look at the green trajectory. We have 3 of them. We have also made very good progress in decision making using machine learning models. So here we have raw sensory input. Our deep learning model is going to produce raw control commands. Well, this doesn't mean that we have to use a giant black box deep learning model. It could be very modular. Well, this is an imitation learning model in action. Again, deep learning models, even in this inclement weather conditions, we can do pretty good lane following. Well, have we solved all the problem? Are we going to see self-driving cars around us immediately? Well, there is a rule in autonomous driving that if you solve 90% of the problem, right, it may take 10 times more effort to solve the rest of the 10% of the problem. We can claim that we probably solved the 90% of the problem. Well, we still have the last 10%. Well, some say, no, it's not 10 times more effort. It's actually 100 times more effort. Whatever that number is, orders of magnitude more effort that's needed. What gets us to the 90%, those techniques will likely not going to be the techniques we're going to use to solve the last 10%. We have huge challenges ahead. We need fundamental breakthroughs in many problems. Here, I would like to point out a few. If you look at the representation that deep models learn, right? And these are not representations that's robust and abstract. It's unlike our human learned representations. If you look at the stop sign, right? People just use black and white stickers and put it on top of the stop sign. And the machine learning model will not recognize it as a stop sign. Instead, machine learning model is going to say this is a speed limit at 45 miles per hour. And in all the images that the researchers try to attack, and all of them are very successful. And the classification score is very confident. We cannot put the self-driving car with these deep learning models on the street. What we need to do? We need to learn robust and abstract representations. While our human vision system are robust against these attacks, can we gain insight from how human visual system processes sensory input? Well, you have seen the complex situations, right? We need to understand the scene, understand human action and the intentions. People are very good at reading other people's intention during driving. This is not the case for the current deep learning models. We haven't made much progress in scene understanding. Well, finally comes the challenge of decision making. If you think about it, our brain is general intelligence. We make very good decisions if we pay attention. Well, we haven't achieved artificial general intelligence. We probably not going to need artificial general intelligence to solve the self-driving problem. But we have a huge challenge. How should we make sequential decision making? Right? Current planning has assumed other human agents just as passive. Although they move, they have their future trajectory, but we can plan through them assuming they're just passive. This gets us to the 90%, but it's not going to get us to solve the last 10%. What we need is a framework for sequential decision making in a multi-agent environment where we can model the behavior of other human agents, and jointly construct the driving policies that can drive us through the real world and handle all the complex situations like we saw in the video. Okay, thanks very much.